Change data capture is a topic that I am passionate about. I hope to get you passionate about it too. Postgres, it's a relational database. Kafka, it's a data store thing. And we'll learn about it today. So if you know nothing about Kafka, this will be fun. Also, if you know nothing about change data capture, this will be fun. There's going to be a live demo involved. It's going to be glorious. I am Jeff Klukas. I'm a data engineer at Simple. If you've never heard of Simple, there's a marketing spiel up here on this slide. It's the whole idea of banking remade with lovely design, equally lovely tools to help you save right inside of your account, and genuine human goodness. It's a pretty cool product. From a technological standpoint, you can think of us as we're the first bank born in the cloud. We were founded in 2009, and we have been Amazon Web Services infrastructure since the beginning, and still are. So I have a bias towards the cloud. My particular role, as I said, I'm a data engineer. I'm also the technical lead for our data platform in general. So that team is responsible for operating Postgres and Kafka. We're also responsible for data pipelines and serving business intelligence users, getting data into our warehouse. I'll talk a little bit about that. The pipeline I'm going to talk about today is it's become a super important part of our infrastructure, both for how our services work and for how we do analytics. So what are we going to talk about? We're going to talk about this data structure idea called a commit log. I'll explain what that is. And it's a pattern that shows up in a lot of different data stores. And we'll see how commit logs relate to Postgres. And we'll see how commit logs are really the foundation of Kafka, this other data store. We will do a live demo of Bottled Water, which is an open source change data capture pipeline from Postgres to Kafka. And then we will look at some of the details of how Simple uses this whole thing. We're going to be a little bit light on that. I really want to focus on the concepts here rather than the details of what we're doing. But I want to motivate. It's a pretty powerful pipeline, and you'll see kind of how it's just pervasive for us at this point. So you ready to learn about commit logs? Let's bring it on. So a commit log it's an abstract kind of concept of a data structure. You can imagine it's an ordered sequence of records. You always append things to the end of it. It has this word log in the name. When you think of logs, you probably think of system logs. Those files that exist on your server, and your application writes a bunch of information about what on earth is it doing right now. And if you think about some of the properties of that log, really if you take this thing that's on the screen and you rotate it, it looks kind of like a log file, where you're always appending things to the end of the file. It's scrolling up your screen. Things are freaking out, and you're trying to figure out what's going on. But there's some properties of that server log and the way that data is going into it. First of all, it's ordered. So if you have a single thread of a single application that's writing to this single log file, those messages are going to end up in the log in the order in which the application wrote them. There are probably timestamps attached, and you're going to see those timestamps increasing as it goes on. It's immutable. There's no real concept of going back and changing what happened in the server log. You're just saying, hey, fire it. This event happened. It's in the log, and that's something that you go back and reference later. And it's durable. It's something that's actually ending up on disk. If the server goes down, it comes back up, and you're able to read that file. Those are the same properties of commit logs in general. And as I'm talking about them in other systems as well, you can kind of think of those same properties of what happens with a server log. So I said this is immutable. We're always appending to it. It kind of grows forever. That might be a problem. You can't have it grow forever. So in practice, what do you do with server logs? You probably roll over to a new log file every day or on some time period, or when it hits a gigabyte in size, you might compress it and send it off to some other system or delete it off of the server. And in practice, this is a concept that happens in other systems that are using commit logs too. So kind of logically, it's this whole history from the beginning of time. And once you write records, they stick around forever. But in practice, you're eventually going to clean up some of those old records, and they're not going to be available on the system anymore. So let's talk about our friend Postgres. Postgres, it's a relational database. It has these tables. You insert records into tables. You read information out of tables. So it doesn't look like it's a commit log, but there is a very important commit log lying behind the scenes when you're writing data to Postgres. If you're a developer and you work with Postgres, you may have never heard of write-ahead logging. If you're an administrator, you probably have heard and think deeply about write-ahead logging. So what is this? I'm going to give you a blurb from the Postgres docs because they say it well. So WAL's central concept is that changes to data files where tables and indexes reside must be written only after those changes have been logged. That is, after log records describing the changes have been flushed to permanent storage. So you didn't know it, but behind the scenes, Postgres is writing to this write-ahead log, which is a commit log, before it ever changes those tables that you're actually accessing. And this is a really important part of how Postgres maintains durability. If you think about, like, Postgres has transactions. A lot of relational databases have transactions. And within a transaction, you open it. You might write 12 different records to 12 different tables. And then you commit the transaction. And you expect either that entire transaction is going to happen, or it's going to get aborted, and it says, sorry, that didn't work, and none of those changes happened. But you're hitting 12 different tables. Those all are happening in different files, actually sitting on the file system. So if Postgres starts into that update, makes changes to 2 of those tables, and then somebody pulls the plug on the server, it goes down. When it comes back up, it's now in a corrupt state. Some of those changes have happened, some of them haven't. And the way that Postgres protects against this is that it realizes, hey, I'm in a corrupt state. I'm going to go replay what I've already written into the WAL to make sure that I get it back up to a consistent state. And your logic is all happy. So it's really kind of the WAL is this data store behind the data store of Postgres that's recording all these changes. So every insert, every update, every delete has this separate record inside of the WAL. And it's this whole event history that's being kept by Postgres. So this is exactly what we want. When I'm talking about change data capture is the concept of getting a full stream of events out of a database like that. So the WAL is already what we want, except it's in this format that exists for Postgres to be able to do stuff with it. It's in this format that's talking about where are things on disk. It's not something that we can interpret for other uses. So back in 2015, Postgres 9.4 introduced a new feature called logical decoding. And this is what the Postgres docs say about logical decoding. It's the process of extracting all persistent changes to a database's tables into a coherent, easy-to-understand format, which can be interpreted without detailed knowledge of the database's internal state. So the pipeline I'm talking about today is using this logical decoding feature. It's basically as those changes are being written to the log, you can also have an output plugin that's installed in Postgres that is additionally writing those messages in some format that you actually want to extract to another system. For our purposes here, it's going to be a JSON format. So there's an output plugin. It's some C code that you add as an extension to Postgres. It lets it know how to translate records into the format that you want. And then you end up having a client application that connects to Postgres on what's called a replication slot. And then that replication slot, Postgres is storing some state about where are you in the changes that have happened to the database. And Postgres is able to ship those changes in the format that you want to your application. So that is the commit log that's lying underneath Postgres is that that write-ahead log that Postgres uses for its own uses for recovering to a consistent state. It also uses that for replicas, other Postgres instances that are mirroring the changes in the main database. And logical decoding is this other way of extracting changes and getting them to a format we can use somewhere else. So in our case, that other place we want things to go is Kafka. So what on earth is this Kafka thing? Do any of you use Kafka? All right. Have others of you heard of Kafka, but you have no idea what it is? Good. OK, so Kafka, it is a data store. It bills itself as a distributed streaming platform. But this is kind of a recent rebranding. If you looked at the Kafka docs about a year ago, it said Apache Kafka, a distributed commit log. So big surprise, commit logs are involved here. And it really is, like, Kafka is a data store that takes this concept of a commit log and kind of puts it front and center, and it's the thing that you interact with. So in Kafka terminology, a single commit log is called a topic partition. These are grouped together into logical topics, hence the name. But the topic partition is the fundamental unit of data storage, and it's the thing that, under the hood, everything is interacting with. So what does a topic partition look like? Again, it looks like this commit log that we've seen in other images. And in this case, these numbers on them are actually significant. Kafka calls those offsets. So when you create a new topic partition, the very first message is going to be assigned to offset 0. The next message will be offset 1, then offset 2, and on and on. That's how Kafka knows about indexing where it is in a log. So there are clients that connect to this, producers and consumers. And producers, they're talking to Kafka. They are saying, hey, I have this bucket of bytes that I want you to write to this particular topic partition. Kafka accepts those writes and appends them to the end of the log. It will, whatever order it receives and accepts those writes in is the order in which it's going to write them into the log. At the same time, you can have multiple consumers consuming from that topic partition. And when a consumer connects to a topic partition, basically all it says is, I want this particular topic, I want this particular partition number, and I want to start at this particular offset. So again, the offset is that number of the record in the log. And when you attach to an offset, Kafka is going to start just sending you big batches of records until you get up all the way to the end of the log. And the consumer has a poll loop where it's continually asking, hey, do you have new information? And Kafka, once you get to the end of the partition, Kafka will send you, new records as it has them available. So different consumers can attach at different offsets, and that's how you interact with it, producers and consumers. If you're familiar with message queues, things like RabbitMQ, other things that are using the AMQP protocol, this looks a lot like it, a lot like a message queue. A fundamental difference here, though, is this idea of attaching at offsets. And that's really all of the tracking that happens. So in a message queue like RabbitMQ, the broker has to keep track of which messages have I sent, and it's really doing it message by message. And your consumer has to send back acknowledgments saying, like, yes, I got this message, I processed it, you're good to go. And it'll be removing messages as they get consumed. In Kafka, Kafka has a whole lot less responsibility on the broker side. Just when you attach as a consumer, you say, I want this offset. And then Kafka is going to give you everything after that. And it's kind of up to you as the consumer to make sure that you've processed all of those records and that you're keeping track of where you are in the log. So we're going to zoom out a little bit. This is an individual topic partition. Now, topic partitions can be grouped into topics. And this also gets to the distributed nature of Kafka. So Kafka is designed to have many brokers in a cluster. So a broker is a server in the Kafka cluster. And if you create a topic, so when you create a topic, you can say, hey, I want to have a topic named foo, and I want it to have 3 partitions. And it's going to create those partitions across different brokers in the cluster. So this particular topic here has 3 partitions. Each one of those is on a separate broker. In Simple's case, we have a pretty small cluster of 4 brokers. So this is realistic for us that you'd have a single topic that's spread across multiple brokers. Writes come in, and they can be round-robined to different topics. But usually what you want is that you want to set a key on the message when you write it. And that key is used for routing it to a particular topic. So let's imagine that we set the user ID as the key of the message. What that means is that the user ID for Alice, every time a message for Alice comes in, we are ensured that it will always go to the same topic partition. So if Alice goes to partition 0 the first time a record is written for her, all of the other records related to Alice will be written to partition 0. This becomes super helpful when you have a distributed application that's consuming, and consumers also know about this multiple partition thing going on. There's a concept called consumer groups, and you can have multiple instances of your application all connecting to Kafka, and Kafka will figure out, okay, I'm going to distribute these partitions amongst you, and maybe one instance of your application is only getting records from partition 0, and each of your instances is then effectively servicing some subset of your customers because they're all, your user IDs are determining where they go in the partitions. So cool, that is the topic. And we talked about, with commit logs in general, they just grow and grow and grow. You're always appending records to the end. In reality, you have to get those off of disk sometime. So the default behavior in Kafka is it's a time-based retention. So this is different from message queues. Message queues are keeping track of where are all my consumers, and then it'll get rid of messages as fast as it can once all the consumers have consumed them. In Kafka, by default, records stick around for 7 days. So that's an interesting piece of durability and flexibility in that you can have some consumer 3 days down the road that then is able to see a bunch of history of what's happened without knowing about it beforehand. But that's the default behavior. There is another type of behavior called log compaction that you can choose on a per topic basis. So what does a compacted topic look like? Instead of time-based retention, it will retain messages based on key. So when a new message comes in with the same key as an old message, those old messages with that same key are eligible for being ejected and removed from disk. So at the top here, we have, this is probably too small to read, so I'll go into some detail here. We have what a log looks like before compaction. There are values. The values in each of these cases are different, V1 through V11. But the keys are sometimes repeating. So if we look at key K1, that appears at offset 0, it appears at offset 2, and it appears at offset 3. So if this topic is configured for compaction, Kafka is only required to keep that most recent value at offset 3. And after compaction happens, it's a periodic process that's running. You'll end up with those initial values for K1 at offset 0 and offset 2. They're removed from the log, and you only have offset 3 left. So what this looks like afterwards is that you only have the most recent key, or the most recent message for each key. And this looks a whole lot like a database table with a primary key on it. So logically, this is exactly the same thing that Postgres is doing with its wall. So if you open a transaction, you insert a record, you update it, you delete it, you insert it again, you update it again. Those are each individual messages in the write-ahead log. But what ends up in your table at the end of the day when you make a query is you're only seeing the most recent version of that row for that primary key coming back at you. So this is a perfect way to model a database table in Kafka in a log compacted topic. So that was a bunch, and also if there are questions, I'm totally okay with taking questions during the talk. The next step of this is that we're going to go into the live demo. So if there are any questions you have at the moment, before we see the world fall apart in a terminal, this is your chance. Yes?
So you're just pointing all your consumers at the Kafka instead of at the SQL server? Right?
Yeah, so the question is, so we're pointing consumers at Kafka rather than the SQL server. Yeah, so in our case, we have a microservice architecture. It's only, the service that writes to the database is the only thing that's able to read from the database. And if anything else outside of that microservice wants to find out about what's happening, then they go to Kafka to hear about, hey, this service is doing this other thing. Question over here?
The use case on all of your slides seems to imply a single or externally coordinated writing source to each topic partition, but multiple readers is Kafka, I've heard of Kafka, but I'm not that familiar with it. Is it capable of guaranteeing monotonicity and atomicity of writes from multiple sources? Or is that left
So-
to the student as an exercise?
So the question is about, is about writes coming from multiple sources and what guarantees are there around that. I'm not going to get into that in this talk, but we can talk about it afterwards. So in general, if you have multiple producers going to a topic, those might come in whatever order. There are tricks you can do, and there's a new feature recently of a concept of transactions with Kafka. It gets crazy, it's cool. It's also very new. So one more question, and then we'll move on. Yep.
Yeah, did you see, are there any known pitfalls or anything to watch out for consumers with persistent connections?
So things to watch out for consumers with persistent connections. Tell me more.
Sessions timing out, and you've got a consumer that's still in a loop using that session, maybe some client libraries don't always have it.
Sure. Yeah. So. Sure. So the main library that is included with Kafka is their Java library. That's kind of like the default consumer, and there are other libraries that are kind of mimicking the behavior. But what's implemented there for consumer behavior is so I said it's kind of the application's responsibility to keep track of where it is, like what offset it has consumed. Kafka does provide actually a nice mechanism around tracking offsets now of, like within that consumer code, you can have it commit offsets to a special topic in Kafka, and it kind of hides all that from you. But it is very important to understand the details of that, of how the consumer loop works when you're committing offsets. And there's a heartbeat mechanism too with the clients, so that the broker will eventually, like if it doesn't hear from a client for, by default, like a minute, something like that, it will consider that consumer dead. It will allow those partitions that were assigned to that consumer to be read by some other instance in that consumer group. But this is getting into details that are kind of beyond the scope of what I'm planning to talk about in here. So I'm going to forge ahead with the demo, and we can get back to these things at the end. I'll leave some time for questions at the end. So bottled water. Created by this gentleman, Martin Kleppmann. I love him. He has some writings which are fantastic. He is a researcher in distributed systems at Cambridge in the UK. And you'll see him at conferences on distributed systems all the time. But he was, so he's an academic, but he also has some history in the startup world. I believe he spent some time at LinkedIn. Kafka came out of LinkedIn. It was developed at LinkedIn. It was open sourced. Then the engineers that made Kafka left LinkedIn, and they have a company called Confluent now they're the main maintainers of Kafka. But anyways, Martin Kleppmann knows those folks. He was supported to write this kind of proof of concept of a change data capture pipeline from Postgres to Kafka. And that is what we're going to show here. So I'm going to demo that. We are going to mirror the display. Everything is going to work perfectly. We have a terminal. All right, I'm going to clear this. Dismiss tip. I'm going to clear this. All right. So we're going to go over to Chrome here. So bottled water PG, this exists on GitHub. I forked it for the purposes of this talk. I changed some of the tutorial details to match what I want to show you today. But most of the content here in this README is from the main Confluent Inc. bottled water project. Most important thing to note is I'm so thankful that they actually put this note here now, because it was in limbo for a long time. It seemed like this was going to evolve into this is going to be the Postgres to Kafka pipeline, but nobody was working on it, and they finally declared it dead. So don't use this in production. But they do helpfully link you to Debezium. I will mention that at the end. Debezium is really the open source solution that exists today that will let you do what we're talking about here. It's a much more complicated project, though, than bottled water, which is why I am demoing this today. So we're going to jump to it. They have this whole Docker Compose set up. I don't know a whole lot about Docker, but I can run the commands that are in this README, and that's what we're going to do today. So I'm going to start copying and pasting stuff. So first, this is just setting a bunch of parameters that are going to be sent to Kafka when we start that up. And then we're going to start up some services. So if you've never seen Docker, it's a thing. There are containers. It runs a bunch of stuff on your machine. Docker Compose is a nice wrapper on top of Docker where you can have, you have a YAML file and you define, I want all of these containers to work together. And it's a way for orchestrating a couple of containers to all run on the same machine. So in this case, we just told Docker Compose, look at your configuration file and spin up Kafka, the Confluent schema registry. Don't worry about that part. We aren't going to talk about it. It's a detail here. And Postgres. So we got Kafka and Postgres running now. We are going to verify that those are indeed running by running Docker Compose PS. It tells us, hey, we've got Kafka, we've got schema registry, we've got Zookeeper going on here. Postgres bottle water. And we'll see if this works. And then what I'm going to do next here is I am going to create a topic. So this is a wrapper around, there's a command line tool that's included with Kafka called Kafka Topics. And this is a way that you can create a topic from the command line. There are some configuration options in here related to compaction, just to make this easier for this talk. But I'm telling it I want one partition for this topic, and I want it to have a replication factor of 1. Kafka's got a cool replication mechanism built in, so you can have a partition replicated to multiple brokers. And that's important if you want consistency in the case of various failures. So we ran that. We created this topic test. It told us, great, things look good. Now we are going to actually log into our Postgres instance using the lovely PSQL tool. I'm going to clear the screen first. So this should get us to a PSQL prompt. Great. We have this nice pristine Postgres instance. No relations found. There's nothing in here right now. So let's create something. We're going to run these commands in Postgres. So what did we just do there? First, we create extension bottled water. This instance of Postgres has the bottled water output plugin available to it. And this is something you do in Postgres to enable an extension. So this is enabling the bottled water output plugin. And then we're creating a table called test. And it's just got these two columns, ID, which it's automatically incrementing that every time we insert a record, and a value called text. So let's select star from test. And this is what our table looks like right now. Now we're going to step back, and we are going to start up the bottled water client program. So this change data capture pipeline, one side of it is on the Postgres side, you set up an output plugin. It has a logical replication slot on the Postgres side. But then you also need some client application that's connecting to that and pulling this data out. So that's the responsibility of this bottled water client application. It's connecting to Postgres, pulling those records out of the change stream, and then it is producing to Kafka. So this is a client that's pulling things out of Postgres, producing them to Kafka. And we will start this up, and we'll just let this sit there and do its thing. It's listening for changes in Postgres as they occur. We're going to just check the logs, see if it looks like that worked. All right, snapshot complete, streaming changes. That's good. This is going better than my tests have gone. All right. Next, what we're going to do is, so I said the Kafka topics executable is something that's included with the Kafka distribution. They also include this Kafka console consumer executable that you can use to consume Kafka messages on the terminal. So we are going to run this now. So we're going to clear over here. going to paste that in. So we're telling it, I want to consume from Kafka. I want to do it from the very beginning of the topic. And I want to show the keys along with the messages.
So in essence, this is basically a tail minus f.
The question, yeah, in essence, this is a tail minus f on the topic, except we're also making sure we're going all the way to the beginning of the file as well, or the beginning of the topic in this case. And I'm telling it that I want to connect to topic test here. So you look at that. So there's something on there. So we did things right. This was actually connected. So this is reflecting this one value that's in the table so far. The format here is that this is a tab, this highlighted space right here. And the format is it's showing you the key of the message, then a tab, and then the value of the message. So you can see here the key that is put onto these Kafka messages is a JSON formatted blob that is just representing the primary key, the value of the primary key for that row. So in this case, ID is the primary key. It's telling us the ID has this value of 1. This is a little bit of a weird JSON format. Why is there this map inside? Why isn't it just saying ID:1? Why does it also have this int in here? This is because bottled water is actually using Avro, which is this cool wire format that, it includes a wire format. You can define schemas with it. But it also has a JSON representation. So this is the JSON representation of an Avro record. And this is the way that they decide to do that, because they want to include the type information along with the value. This is how they've decided to do that. The value looks very similar to the key. It's that same Avro JSON format. But in this case, it also contains all of the columns, not just the primary key. So let's right into this. Insert some more rows. Let's update a row. Update test set value equals modified where ID equals 1. So you see another message appeared in Kafka. Again, it's telling us the primary key is this value 1. And we see this new modified value here. So every insert, every update, every delete will show up in that. I'm going to insert one more new record in here. And then I am going to close down this consumer. I'm going to start consuming from this topic again. And I want you to ask yourself, what do you expect to see when we connect again? So I'm telling it I want to consume from the beginning of the topic. We're doing all the same things. This is the exact same command that we ran before. So when we connect to the beginning of the topic, what do you expect to see down here? Let's see what happens. Log compaction is turned on for this topic. So yeah, so that's the important question. I wanted to demonstrate here log compaction at work. You'll notice that this record with primary key 1, we see this modified value, but that very first record that we wrote in, it's now been cleaned up by compaction because we got this update in. It had the same key as that first message that we wrote in, so it became eligible for compaction, and compaction ran and cleaned it up. Yeah, question?
How do record deletes?
That is the very next thing that I'm going to show you, is what deletes look like. So let's decide we really don't like this table anymore, and we're just going to delete from test. So you can see there, in Java, this is literally you produce a null as the value of your message with a given primary key, and that's used as a representation of a delete for this concept of log compaction. There's a question back there.
Yeah, let's say that you wanted to see changes, though. Is that auditable? Someone updates that value to modify.
So the question is this auditable? This has been cleaned up off of Kafka at this point. So if you're relying on Kafka, that record doesn't exist there anymore. I will show you in a bit. Like in our case, we have another service that is reading from these things, and it's archiving topics to S3. So we do have like a full audit history of what's happening in these topics being persisted to S3. All right, I'm running out of time here. So we just did a bunch of deletes. I'm going to do one more insert. I'm going to ask you the question again. We're going to shut down this consumer. And now, what do you expect to see when we connect again? I'm hearing somebody say they expect just the 7. You are so right, but you're oh so very wrong. This is just another detail here. Those nulls all stick around. This is a detail of those nulls can be considered a tombstone record. And there's some details of if you have a consumer that's falling a little bit behind and a delete comes in, and that delete gets cleaned up before your consumer has read the delete, then it's never going to know that that record was deleted, and you can end up with a corrupted cache. So nulls are handled in a special way. They are kept for 7 days, even if they're would otherwise be eligible for compaction. So that's the live demo. That worked really well. I'm happy. Thank you for being engaged. Always exciting. All right, it is 1:40. So I want to be cognizant of time. I want to leave some time for questions at the end. So I'm going to try to finish up here. The last thing that I want to talk about here, I meant to skip over these. This was just in case the demo didn't work. I had some backup slides. So use cases. What does simple actually do with change data capture? So we do not use bottled water. We would be in kind of bad position if we had committed to bottled water at this point. We ended up writing our own Postgres to Kafka change data capture pipeline. It's similar to bottled water in a lot of ways. We are looking to maybe open source it at some point. But we also have a blog post that goes into a lot of detail about design choices we made that are different from bottled water. I will link you to that blog post later in here. But I want to give you a sense of the overall flow of what happens in our system and how powerful this is. So you probably won't be able to read the text on here. They're like really tiny labels. I will tell you what's going on. We have a microservices architecture. So the fundamental unit looks kind of like that thing that you see there, where the orange part is a service that could be multiple instances all running the same application. And they're all talking to a single Postgres database that is just for that service. In this case, this is our transaction service. We have a backing bank that actually holds accounts. When transactions happen, they get sent to us over a message queue, and this transaction service is what does our bookkeeping about what's going on with transactions. That Postgres instance has a kind of co-service sitting next to it on another instance. Again, this is all in AWS. We call it PG Kafka is the name of our change data capture pipeline rather than bottled water. So that Postgres instance has an instance of PG Kafka that is subscribed to a logical replication slot. It's sending all of those records to Kafka. One of the most important design decisions that's different from bottled water is that, so if you think about the write-ahead log in Postgres, there's just one write-ahead log for the whole instance. Each record would be like, I'm inserting a record into table X with value Y. The next record could be, I'm inserting into table Z with value 92. And we've decided to model that directly in Kafka. So we just write to one topic for the entire instance that's multiplexed all of those different tables together, which has some advantages. It also has some disadvantages. Sometimes you really only want to know about that one table. So one thing that we've done is we have a service that we call demux, our demultiplexer, that consumes from that topic and writes out records per table to a bunch of other topics. So this takes in the transactions PG Kafka topic. It writes out just the transactions table to one topic and the customers table to another topic. Then we have another service, our user activity service, that cares about knowing about these transactions coming in. So when you open up the simple app, the main page that you see is, these are all your recent transactions. The way that it finds out about that is by consuming from this transactions table topic in Kafka. It ingests those messages. It writes those to its own database. That database also has an instance of PG Kafka, and those changes are getting sent to Kafka in a separate topic in a different format that's appropriate for that service. And while this is all going on, we have a whole analytics infrastructure that is reading from all of these PG Kafka produced topics. It's archiving them to Amazon S3 so that we have a kind of source of truth of what happened to go back to. And we're also putting those into Amazon Redshift, which is our data warehouse that we use. And that's the basis of like 75% of what our business intelligence and data scientists users, they're using this data that is derived from this whole pipeline from Postgres. So just high level, what are the pieces here? There's that core change data capture pipeline, that part that's actually an application that is reading from Postgres on this logical decoding slot and is producing the messages to Kafka. This is a form of messaging between services. If you'll notice, the transaction service doesn't know anything about Kafka at all. It's just writing things to its own database for its own purposes. And it's a separate process that is consuming those changes and writing it to Kafka. So it's pretty cool that this user activity service can consume from that without the transaction service ever having to worry about Kafka. And this is, in practice, this is how services do asynchronous messaging in our infrastructure. This is how you know about what some other service is doing, is you subscribe to its log of changes in the database. And then finally, our analytics is powered by this. So to recap, commit logs, they show up all over the place. They are really central to how Postgres and other databases maintain durability. MySQL has something called the bin log, which is analogous to the wall. And the bin log is also available for doing this sort of logical decoding thing. And there are solutions for MySQL as well. Kafka, it's cool. It's really commit logs as a data store, distributed, and it can handle huge amounts of data if you have a need for that. We saw bottled water, and we talked a bit about how simple it uses this. So I want to leave you with some resources if you actually want to do something with this or you want to learn more about the concept. Again, all the hairy details about how Simple has decided to implement this pipeline, comparing that to bottled water is in a blog post on simple.com/engineering. Bottled water itself, looking at the repo, and there's a blog post that Martin Kleppmann wrote for Confluent, which is it's really fabulous kind of overview of the concepts involved. If you actually want to implement this, Debezium is the project to look at. It is a change data capture pipeline to Kafka from multiple sources. So it has connectors for Postgres, MySQL, and MongoDB. And it's something that there are actual people that use in this world. WePay, in particular, wrote a blog post about their MySQL to Kafka pipeline using Debezium. And they also gave a talk at the Kafka Summit this summer. And those are great resources as well. Martin Kleppmann, I mentioned him earlier. He's the bottled water author. Everything he writes, I love. But the Making Sense of Stream Processing ebook is available for free and goes into a lot of the kind of theoretical detail on a lot of these concepts as well. So we can go ahead and do some final questions before we close. All right. I am going to take in the front. Yes?
There's a bunch of servers pulling JSON records and then making database records from them that originated as database records, which strikes me as weird. Is that much load or a lot of programming work, or is that just trivial?
Yeah, so the question is, it seems a little bit strange that we're taking records from a database, they're going through Kafka, they're ending up in another service, and they're getting written to the database again. So load-wise, like we don't have very high throughput, at least in Kafka terms. Our throughput is not really a problem, and we've been easily able to handle that. And the decoupling that allows between the different services has been pretty nice. Keeping track of schemas is not so easy. JSON doesn't give you a whole lot of help in that. So like our pipeline that we use internally, it is JSON based. Schemas are kind of inside the message, but there's no central registry. And that's another piece of bottled water that I didn't talk about. There is this schema registry that Confluent provides. Avro has this whole concept of you write your schema to the schema registry. The schema registry will yell at you if you try to write records that don't fit that schema. And schema management is is a problem that we grapple with sometimes, and we haven't totally figured it out. But I would love to get to a point where we're using something like the schema registry for doing more of that management of what's happening in different services and documenting it, hopefully.
I think my question is about the same, but if you did a wall forwarding to a second SQL server, to a second Postgres server, what advantage do you have this method over doing that?
Yeah, so what advantages do we have doing this thing rather than going directly from one Postgres to another Postgres using WAL? So one thing, okay, so transmitting WAL from one Postgres server to another Postgres server is known as physical replication. That is something that's an all or nothing concept of like, you can use that to create a replica of the database, but you have no control over, if you only want this one table to appear somewhere else, you can't do that with physical decoding. One of the new features in Postgres 10 that either just got released or is getting released in like the next couple of days is called logical replication, where it's using this logical decoding new thing of putting things into a logical format, and you can say, I just want this one table to be sent over the wire to this other Postgres instance, and have the table appear there. So that's an option that we could explore. I think like the flexibility of just sending everything to Kafka, not worrying about the schema on the other side at the time that we're writing it, has been pretty flexible and beneficial for us. All right, I have a question in the front here.
So you're going to grow.
Sure, we're gonna grow.
And you're going to outgrow your 4 Kafka brokers.
Mm-hmm.
But they all split everything up by customer ID and they took every 4th one. What happens when you add another one?
Okay, so yeah, the question is, as you grow, what happens, like you've decided to lay out your data the way it is. How do you manage adding additional brokers to your cluster? So in our case, we're doing like a super simple thing of like each of our, almost all of our topics are just one partition, and we don't do any like partitioning between different brokers. That obviously won't last forever. But if you do, it's really hard to increase the number of partitions on a topic. In fact, with Kafka, it's impossible to increase the number of partitions that are assigned to a topic. So if you get to the point of like, I need more partitions, you have to just create a new topic. So that's best practices is if you do want to do this thing of having multiple partitions in a topic, create way more of them than you ever think you're gonna need. And then it is really easy, as you add new brokers to your cluster, it's pretty easy to rebalance the partitions across more brokers, as long as you had it split out to a bunch of partitions in the first place. And Kafka, like topics and partitions are super cheap for Kafka, so it's totally feasible to have many hundreds or thousands or tens of thousands of partitions. So you can create a topic with 100 partitions, and really you only care about, like you only have 2 instances of your app, so they're each consuming 50 partitions. It seems a little silly, but there's really no overhead to doing that. And so yeah, so best practice is to create way more partitions than you think you're gonna need. I will take one more question if there is one in the back.
Is the compaction guaranteed upon the next read, or is it something that will happen eventually if you have a really hard?
Yeah, the question is compaction guaranteed, like for the next read that you won't see those old messages? No, it's something that happens in the background periodically, and there are a bunch of tunables as far as like how often it runs.
Special for the demo to make it appear immediately?
Yeah, I did. So when I created the topic, I set a bunch of parameters on there that said like, hey, run the, like items are eligible for compaction within 100 milliseconds or whatever. And the default for that is that I think that they're not eligible for compaction for like 8 hours or something on that order. So if you have consumers that are within a couple of hours of real time, then they generally will never see the effects of compaction, and they're going to see the whole list of changes as they come through. All right, thank you so much.